Hi, I'm Esther.
And I'm Sean.
I write about AI news here at Tech Target.
And I edit Esther's stories.
We're here to talk to tech experts about everything AI, from open and closed models to AI agents and who's ahead in a generative AI race.
And even the elusive AGI.
We've got it covered, right, Sean?
Yep, we've got it covered.
Hello, everyone. Welcome to another Targeting AI podcast. Today, our guest is Kevin Dearlin, Senior Vice President of Networking at Nvidia. Before Nvidia, Kevin was the Senior Vice President of Marketing at Mellanox Technologies and Vice President of Technology at Genia Technologies. Thank you so much for joining us today, Kevin.
Hey, it's great to be here. Thanks for having me.
So to kick off, one of the things I noticed that you have been working in technology, particularly hardware, for a very long time. You started in engineering. What led to your interest in chip design and AI?
Well, chip design goes back to being a kid. My father was at Fairchild. I went to Berkeley and studied physics because I did not want to be a double E like my father. But I went through on a Fairchild scholarship and hit the ground running and became a chip designer intentionally, but absolutely loved it. And then I joined NVIDIA 5 years ago when Jensen had the vision that networking was going to be super important for AI. And ever since then, I've really enjoyed learning and developing AI solutions as part of our platforms.
Okay, so I guess we'll jump right into AI factories. I am interested in networking for AI too, but so there's been a lot of discussion lately about AI factories, compared to data centers. It's an easy way to conceptualize it for a lot of people, like, oh, it's a data center on steroids for AI. But can you actually expand on the difference between a traditional data center and an AI factory, and also tell us what do AI factories produce? I understand you guys say it produces intelligence at scale. But what does that mean in practical terms? And what hardware is needed to make these places work about beyond GPUs? Sorry, like three questions here.
Yeah, but I think that those are great questions because, traditionally when we think of factories, you have inputs that come out and products, inputs that go into the factory and then products that come out. And really, an AI factory does the same thing. And in this case, the inputs that go in is data, and we call that input tokens. But there's all kinds of data. It can be today multimodal data. So in the past, it was enterprise documents and how do we build things. And then now it's really multimodal. It can be cameras, it can be visual, it can be graphs. All of that data is normally something that is very, very hard to understand. And what we're able to do now is crunch it using AI and really come out with knowledge and insights and design new products. So we have input tokens coming in and output tokens going out. It's a new kind of factory. And you asked the right question is what is that required to build that beyond a GPU? And that's what I love about NVIDIA and Jensen and the way we think about an AI factory. We don't think at the component level. It's not just a GPU. We don't throw out a bunch of parts and then expect customers to be able to build something useful because AI is hard. It's hard to deliver solutions and without having to do a whole bunch of foundational training of the models. And more, what we're seeing is that inferencing, in other words, using those models, is becoming agentic. And we're going from what's called system one thinking, which one shot, you ask it a question, it gives you an answer, to agentic reasoning. And that's what humans do. And we're seeing AIs doing that now. And what that means is that inferencing is becoming a lot more like training. And to do that, we need a whole bunch of platforms for every industry. So, whatever type of industry you're in, you actually don't want to go off and try to reinvent the wheel. And that's really what makes NVIDIA unique is develop all sorts of frameworks and platforms so that our customers, no matter what vertical business they're in, whatever industry they're in, they can hit the ground running and take their domain expertise and apply it to this factory. And we give blueprints and reference architectures that helps them stand that up, build it correctly, size everything correctly. The last thing you want to do is start with a bunch of parts and put them together and then find out that you misarchitected things. You don't have enough networking, you have too much memory or not enough GPUs. All of those things need to be sized correctly and matched accordingly to the work that you're doing. So we like to build the reference architectures and the software platforms and libraries and SDKs so that our customers can take advantage of all of their know-how and their domain expertise to hit the ground running and start using AI today. It's going to transform every industry.
I wonder if you can expand a little bit on the your NVIDIA AI strategy with AI factories and which of the latest GPUs, networking, and software are designed with from NVIDIA for AI factories.
Sure. So, the key thing there is we have a whole bunch. I mean, the components are important. What you choose to build out an AI factory is really important. And one of the things that I think Jensen saw before anyone in the world really was that networking was important. So GPUs are important, but the infrastructure that connects those GPUs is vitally important. And so it's 6 years ago now that he announced the acquisition of Mellanox, and we were a leading networking company for HPC, for high performance computing. And it turns out that high performance computing and AI are really almost the same thing. And that's making a bunch of computers behave as a single computer. And the realization that I think Jensen had is that the computer is no longer a box that has a processor inside or even just a GPU inside, but it's actually an entire data center. And making that data center operate efficiently at data center scale, being able to scale up and scale out and connect compute and networking and storage all together very, very efficiently. And so he brought in Mellanox, and we have expertise in switching and in adapters. So our data processing units and the NICs, these are not yesterday's simple little devices. They do actually computing in the network. We do in network computing. We're processing the data as it's moving through the network, and we're making thousands and tens of thousands, hundreds of thousands, and now millions of GPUs behave as if they were a single computer. That is really hard to do. And then on top of that, we build all the software frameworks for all sorts of industries. So whether that's energy or healthcare or trying to design the next generation of automobiles, all of that is actually built together into a factory.
Can you give us a quick idea, a quick follow up on what AI factory physically is? Is it a big warehouse with racks of servers? Is it and just housing GPUs, or can it be distributed? Yeah.
Yeah. So the biggest data centers in the world, these AI factories are indeed, data centers with racks and racks and racks of GPU based storage. But it's more than just, a single computer with some sheet metal wrapped around it. We actually integrate within the rack. We've squeezed more and more of these GPUs together and we scale them up. So we have scale up networking technology inside of that rack. So really, it's a rack unit, and then we can scale those rack units out and make them look like one computer. And so scaling up is really important. We can do that with copper inside of the rack, but the performance of these supercomputers, these AI factories, is so high. The networking performance, we're not talking about something that you have at your desktop in your office or something that you could have at home with a gigabit or 10 gigabit Ethernet. We're talking hundreds of gigabits per second for every link. And when we talk about our scale up platform, we start talking about terabits per second. This is astounding amount of bandwidth. And really, you can think about it as these giant GPUs that have billions and hundreds of billions of transistors in them now operating across that scale up network. And so we can scale them up, we can scale them out, and they become football field size data centers. But you ask, can we also do that with multiple data sensors? And the answer is yes. That really starts to address new types of computing where you have that AI factory that produces a ton of data. It can do simulations for engineering. But then we push those out to the edge, and we're even building federated systems now where you have smaller data centers. So a lot of regions in the world, they don't have these giant football field size data centers, and they have smaller telcos. And so one of the things that we see is that many of our regional partners across the world have smaller data centers that they then need to connect together. And we're doing that too to build out AI factories. And then, of course, we can go all the way to the edge, the far edge, and you've got robots, whether that's a car or the robot that builds cars or builds other things. Those are really edge computing. They're connected back into the AI factory, and we simulate real factories. We simulate the robots in a AI data center that is an AI factory. And then once we have all of that simulation, that we design the robots, we can push them out to the edge and we put a computer inside of the robot that actually runs that. But we simulate it first in our world. And once we're able to do that in the AI factory, we actually can fail fast in the virtual world so that we succeed fast in the real world with all of these edge computing devices like robots and cars and all the things that are coming. It's fantastic.
So, when we talk about enterprises, what would you say that they should know about factories? Why should they be interested in the AI factory? And how does it relate to growing and scaling generative AI and large language models?
Yeah, so I think the key thing for enterprises is they're unlikely to train their own AI models, what's called a foundational model or a large language model. So what they want to do is consume those models, and then they want to fine tune them, and then they want to use other technologies like RAG. RAG is retrieval augmented generation. And the idea there is enterprises have a huge amount of data inside of you know, their finance department, their engineering department, and they want to incorporate that. Here at NVIDIA, we have enormous number of documents on all of our chips and our systems and the software stacks. No person can read every document that we have, but an AI can. And so we can actually ingest all of that data. So in an enterprise, and you actually enterprises don't want to share their confidential private information with a large language model and say, hey, train on this, because what you've just done is exposed all of your proprietary information to that model. And that model can then share that with other people. So you want to do fine tuning of a model, and you want to use technologies like retrieval augmented generation inside of the enterprise. So you're going to take advantage of that AI data factory that's building things at scale. And then in the enterprise, you're going to use a fine tuned large language model. You may scale that up. There's all sorts of choices. One of the things that NVIDIA does well is we partner with everybody. So if you look at all of the large language models out there, whether that's Llama or Mistral or DeepSeek, often what we do is take those open source models and we distill them and make them better. So keep it as open source. We have something that's called, for example, Llama Nematron, which today is the best model out there. And we combined multiple models. We took a Llama model from the standard open source Llama model that was produced, and we added reasoning to it. And by doing that, it actually becomes a better model. And so, really, we see just a virtuous cycle of people continuing to make better and better models. And then we open those up and we support all kinds of different frameworks that let different customers use whatever they want in just their enterprise data and start, asking questions of their data. They talk to their data. And so that is really powerful because, like I said, I can't read a fraction of the documents that we have internally, but I can ask an AI to do that for me and do deep analysis. And we can actually go back and do deep research. And if you do those kinds of things, you'll see it. And we can actually ask it, tell it to turn it on. We have something called build.nvidia.com. You can select a model, any of these deep research models, and you can watch the models thinking. You can watch what they're reading, and they'll tell you what they're doing. And you're saying, wow, that would take me hours to read just one of these papers because they're complicated. And then they can start answering questions. And part of what's really fascinating about this, at least for me, is, AI is only as good as the humans that are engaging with it. You're asking an AI model questions, you're learning about your data. What is it that you ask? It's actually an interactive process. It's not something that the model just goes, figures out what you want to know. You have to engage with it. You ask the right questions. And we see all kinds of things where humans and AIs are interacting in just new ways that really wasn't possible before. Huge productivity gain.
Okay, so these AI factories, building them, designing them, operating them, what kind of power consumption is involved in compute resources, and also how does Nvidia handle challenges like chip supply and cost availability?
Sure. So those are really big challenges. One of the things that we do is we build a AI factory ourselves. And so it turns out that in any reasonably complicated system, if you haven't tested it, it doesn't work. And we realized that. And so we actually build these from the ground up ourselves. And we do that because we can do it as fast as we can get the chips. We can just integrate them ourselves. We have all of the people that design the chips and the systems and the networking and the optics. All of that is super, super important. It's high power. As I said, we're making the power lower and lower. That's a critical thing. So when we think about an AI factory, there's two things that we think about. And Jensen challenges us to do this every day. He said, what is your performance per dollar? And what is your performance per watt? Those are the things that we're trying to optimize. So we reduce power. One of the ways we do that is we squeeze those GPUs closer and closer together. And you can ask yourself, why do we do that? Is it because we like to have a lot of heat inside of a data center that's hard to cool inside of a rack? It's not. We do that so we can connect them with copper. So Jensen said at GTC, copper where you can. And as we go faster and faster and faster, the distance that you're able to travel over copper is getting shorter and shorter and shorter and shorter. So we're seeing that happen. And so we squeeze those GPUs together. We've actually implemented liquid cooling in order to do that. And what that does is it reduces the power dramatically because the alternative to copper is optics. And so wherever we can, we use copper and we use as much copper as we can, which is why we squeeze this together. We use liquid cooling now. That's more efficient in terms of the power, and the copper is more efficient than the optics. But when we scale out to 100,000 GPUs, these are football field sized data centers. Those need to use optics. And so we introduce new technologies like CPO. CPO stands for co-packaged optics. We're actually putting the optics right next to the chips. And when we do that, that substantially reduces the power. So power is a huge focus. These data centers are megawatts, in some cases, tens of megawatts. We're even hearing about gigawatt power, you know, data centers. So we have to continue to do what we've been doing, which is deliver higher performance per watt in order to actually keep this something that we can build and do so sustainably. And that's a huge focus of the company.
Shifting gears a little bit, obviously, when we're talking about AI factories, we also can't fail to mention the AI supercomputers that NVIDIA is building. Can you expand on how that is going?
Yeah, so there's a lot of different AI supercomputers. We that's the heritage that Mellanox came from. We have a technology called InfiniBand. InfiniBand is really the world standard for AI and supercomputers. It's interesting. We're seeing the lines blur between AI and supercomputing. So, what traditionally was supercomputing, which was scientific applications, so things like, computational fluid dynamics and proteomics. So, if you're designing an airplane or a rocket ship, or if you're really trying to discover the next generation of medicines and drugs for treatments, all of those things are enormously complicated compute, and they require enormous amounts of computational devices. And then, as I said, we actually connect those together. Our InfiniBand technology has this in-network computing, and somebody likened it to delivering pizzas. How do you deliver a pizza faster? It turns out that you can make a lot more pizza ovens in your factory, but if it still takes a half an hour to cook the pizza and then put it into a car or a truck and drive it to the person's home to deliver that pizza, it still takes half an hour, no matter how many ovens you have in your factory. Well, what we did is we sort of put an oven inside of the truck. So our networking technology is actually doing the processing as the data is moving through the network. And that was a critical function for HPC because we sped up the computation so much. And what happens is all of the computers in an HPC computer are acting as a single computer. And they slice up the data into different pieces. Each of them works on a different part of the data. And then they need to share what they found with that data. And when they share that data, that turned out to be the bottleneck. Once we accelerated everything, it operates really fast. And then there's this long period of time where we're sharing all the information between all the nodes. Maybe you've got 100,000 GPUs in a giant HPC data center. What we do now is while we're sharing that data, we actually do computing as the data is moving through the network. And so that's the analogy of cooking the pizza while it's on the way to a person's home. That actually can speed up how fast we're able to deliver pizzas, or in this case, design the next generation of airplanes or rocket ships or new drugs and things like that. So HPC and AI share that same issue of being able to continue to accelerate as we've sped up computing a million fold in the last 10 years. And so now that last piece of where we're sharing information between all of those computers, we're accelerating that too. So this is really where when Jensen says the data center is the new unit of computing, he means it. We're actually computing across the entire data center.
Okay, so let's shift gears to AI agents. No conversation about AI can fail to include AI agents. Now, even though it's remarkable because a year and a half ago, no one ever heard of AI agents. But I mean, there was RPA bots and stuff like that. But so AI agents often need the ability to perceive, plan, and execute actions. So, are your AI factories optimized to support agentic AI workloads, and how do they do it?
Yes, so that's a great question, and you're absolutely right. It was interesting, you know, a year ago, just a year ago, people were talking about inference, which is when you query a AI foundational large language model and you get an answer. They said, well, that's a simple problem. It's a one-shot problem here. Ask it a question, you get an answer. It runs on, well, maybe it's not one GPU, but it runs on a few GPUs. And it's really simple, and we don't need networking. Agents is completely different than that. And fortunately, Jensen recognized that and got the whole company motivated and working on this years and years ago. It's a long time to develop these chips. So our Blackwell chip that is now ramping into the market is really built for inferencing and for agents. And there's specialized functions that we put in to do that. So agentic reasoning is where you've got multiple devices that are actually operating together. And we actually do a lot of planning, how we're going to approach a problem. And then we call one agent can talk to another agent, can talk to another agent. And there's a whole bunch of things that changes. And of course, networking is critical to that because when you have these agents, they can run in parallel. We can try 5 different strategies, and then we can have another agent that looks at the results from all of them and synthesizes the best results, takes re-ranking, and we can watch the processing and the thinking that's going into that. But we built Blackwell to be able to do that really, really well. If you look at the speed up that we got with inferencing for agents, it's like 30x from our previous generation. And we continue to compound that performance gains through software. So it's not like the first time we ship something with a new generation of GPUs, that's it. That's all you ever get. We continue to improve the software as well. So agentic reasoning is really state of the art now. That's what we're seeing happening. And it's incredible. Jensen gave a great example at his GTC conference where it was actually a fairly simple problem. I mean, something we've all faced, or at least anybody that's been involved with getting married themselves or having a child that got married, or, how do you seat people at your wedding? It turns out there's all kinds of constraints. So and so doesn't like the mother-in-law or the father-in-law, or maybe you've got a young person in the family that needs a child that needs to sit next to somebody else to help them. And if you have all these constraints and you ask a simple inference model, a large language model, hey, seat 9 people around a table or 7 people around a table, it's surprising. It gets it wrong 10 out of 10 times. It ends up sitting the best man next to the newly married bride instead of the husband, the groom. And so we showed that with agentic reasoning, when it starts to think about what it's doing and it's more deliberate and reasoning, then it can solve that problem. It seems like a simple problem, but it actually isn't. And when we compound that to real world problems, I mean, it's easy for humans to actually figure that out. It turns out an LLM, a large language model, without agentic reasoning, can't solve that problem very well. Well, problems are a lot harder than that people deal with on an everyday basis, and agentic reasoning is critical for that. So it's super important that we focused on that starting years and years ago before people realized that agentic reasoning was going to be so important.
I just sort of follow up a little bit on agents interacting with each other inside an AI factory. I mean, can you just talk a little bit more about that? You touched on it. Like, is there? I think there's an emerging field of like agent orchestration, and so how do you get them to not run around chaotically doing without coordinating with each other?
Yeah, I think you're right. If you look at agents that are now all of a sudden, you don't want to just run willy nilly, have a bunch of agents all working without orchestration to actually make things work well together. And it's interesting, if we look at the chatbot with the human interacting with an AI, humans are both very, very slow creatures. Computers make fun of us behind our back, how slow we are. But we're also impatient creatures. And so one of the things that we say is time to first token matters. So when you ask a question, how long does it take to get a response? And that's one of the areas that we're deeply focused on. We introduced new technology called Dynamo. And Dynamo, Jensen characterized it as the operating system of the AI factory. And it really does that orchestration of all of these different agents, and it accelerates the time that we're able to respond, how fast we're able to respond to we impatient humans. So it turns out that when you have a lot of agents that are trying to do something, the time for each of those agents, I mean, it may be that we ask an agents, a dozen agents to answer part of a problem. And then we need to synthesize the results from all of those agents. And only once we've done that, and we may send that back through really a series of processes where we ask a question that generates the next question that generates the next question. And only after doing all of that agentic workflow can we respond to a high level complicated question. And so delivering results quickly is super important. And so Dynamo is this operating system of the AI factory that actually coordinates all of that and makes sure that We don't have, a bunch of agents just operating completely independently, running around in circles and not giving an answer quickly. It's important that we actually orchestrate all of that. And so this Dynamo platform that we built is important. A Dynamo was really the first engine, if you will, and it was critical when we started to take water and generate power back a century ago from electricity generation. Was really the first part of what drove the industrial revolution of the 20th century. And what we're seeing now is the AI factory, Dynamo to coordinate all of those agents is really enabling the next wave of this AI industrial revolution.
Nice.
So, when we talk about factories, I want to wonder what is the cost for enterprises? How affordable will it be for them? And I believe data is a key ingredient in these factories, obviously. So, how will NVIDIA ensure data governance and security?
Yeah. So two parts of that question. The first is, how does enterprises use it? What does it cost? Enterprises will be able to use AI factories in multiple ways. And one of the things that's good here is that some of these foundational models have been open source. The enterprises don't need to build them themselves. They can bring that either on-prem or put it into a co-location facility, similar to what they've been doing today, and consume it at a level of a service. And so they can either build their own AI data factory. Some of the largest enterprises will do that, but they can also, have someone that's offering that. We have a whole bunch of partners now that are really new, the next generation of AI service providers. We also provide it into the big cloud vendors. The traditional cloud vendors are offering what we call DGX Cloud, and they can just consume it as a service. So you don't necessarily need to build your own factory. You can actually go procure a factory that's already been built and just start using that factory. And the second part of your question was related to data and data governance and data security. And those are great. That's a really great point because you absolutely have to secure your data. And I talked about retrieval augmented generation, where instead of sending your data off to train a large language model and in the process of doing that, sharing it with all your competitors, that's not something you want to do. So you'll want to fine tune your large language models with your data privately, and you'll want to use retrieval augmented generation privately. And just as today inside of an enterprise, there's things related to financial reporting, or maybe there's things on your next generation, most secretive products that you want to confine the people, even within your own enterprise, of what you can see and what you can't see. And so you have typically what's called access control lists, have role-based access control and fine-tuned access control. And all of those things actually need to permeate and become integrated into AI. Because if we look at the past, I think it's 25 years ago now that we first started to see the first search engines come out. And I was always hoping that after search, the next thing would be find. It turns out it wasn't. It was something else. It was, maps and videos and all kinds of other great things. But here it is 25 years later, when we search for things, we don't really find them. We get a winnowed list of possible candidates that we then need to sort of sort through. With retrieval augmented generation, it's amazing. It does something called a similarity search. You ask it a question, and it searches through hundreds of thousands of documents and it finds things that answer the question you asked. So instead of having to search individual documents as we're used to doing, now you can search across all of these documents that have been integrated into a vector database. And we do this similarity search. What that means is finally we're going to have find. But that actually raises some interesting questions. It turns out that I may have access to files today that I shouldn't. And now I can find things that I shouldn't. And so we need to be really careful about data provenance, where the data comes from, and the data protection, and bring those access controls, the fine grained access controls into AI. And we're working with all sorts of partners. We developed something called the Nvidia AI data platform. And again, we don't sell end products to enterprises. We work with partners to build those solutions. And in this case, the partners are all of the storage vendors because they're building these appliances now that are really allow you to talk to your data. And so at the AI data platforms from all of our partners, the storage partners, all of the big storage partners, they have the data and now you can query your data. You can find things, you can ask questions and get responses across all of them. But we have to integrate all of the access control list and the protection of that data as part of that. And that's been a key focus is to actually integrate those access controls, the security, the encryption, all of those things. The good thing is what we do is accelerate all of those things. We accelerate encryption, we accelerate the access control list. So we make things faster and our partners make it easy for enterprises to use them.
Thank you so much, Kevin. You've been such a wonderful and knowledgeable guest. Our final question is, how do you expect factories to evolve?
Yeah, that's a great question. You know, I get asked that a lot, and it's fascinating to watch how fast AI is moving. You know, Sean mentioned that just a year ago, nobody had heard of an agent, and today it's agentic AI is all the rage. What I believe will happen is we'll start to see AI more and more with AIs talking to AIs talking to AIs. So today, it's humans, and I think we have to have humans in the loop. As I said before, it's going to be an interaction between humans and AIs. But I think as part of that, the AI that we're going to be interoperating with isn't going to be just a simple one shot answer. It's going to be these complex ensembles of AIs. And one of the exciting things that I see is the multimodal nature of things. So if you start thinking about synergies, often, as humans, it's hard enough to become an expert in one field. I'm an expert in chip design. But how do you become an expert in chip design and biology? And how do you become an expert in, finance or exploration or material sciences? It turns out that AIs can be experts in all of those things. And we can start to see synergies between technologies. And so when we start to see things that potentially humans haven't thought about, where we see interactions between different things. And I think these AIs are going to start talking in a language that today we can watch it. It's language. It literally is English. We can watch the tokens. It's really kind of fun to watch a deep reasoning model. You turn it on and you can see all the words coming out and they're talking to each other in words. I think in the future, we're going to see AIs talking to each other in binary. And I think it's important that humans are in the loop there. And we always love humans in the loop, whether that's with robots or AIs talking to each other, because humans bring a unique capabilities and ethos and emotion and all of these things that are really uniquely human. So I think it's important, but I think that's what we're going to start to see is, robotics, I think is the next layer of physical AI, and I think it's really important that we keep humans in the loop in all of this. And this is something that I think is central. Jensen realizes this and he drives the company to make sure that we've always got humans in the loop with our machines that are operating with AI. So that's what I think is going to be exciting in the future.
That is something to look forward to. So, thank you so much for being with us. You're an extremely able advocate for NVIDIA, which is basically the world's most successful AI company, and really delighted to have you on and to explore this really fascinating new part of the AI industry, AI factory. So everybody can reach Kevin at NVIDIA, and you can see our podcast on wherever you get your podcasts: Apple, Spotify, Apple Podcast, Amazon, Google, and you can also read about it at Tech Target and listen there. Thank you so much. We really appreciate having you on.
Thank you. Thank you, Sean. Thank you, Esther.
To hear the full audio podcast, please go to Apple Podcasts, Spotify, Amazon, Audible, TuneIn, Podbean, and other popular podcast platforms.